So what you should do is, first you should take a trial depth. Let us say you just assume the depth of 1 to 2 meter. You can just assume any depth, or it could be greater also, it depends. So first you start with the assumption depth. Let us say it is 1.5 meter, and based on the formula which you just saw, you determine the critical velocity. V naught equal to 0.55 m d power 0.64. So you substitute this d here, and you may also know the critical velocity ratio for that channel, and you determine the critical velocity ratio. The discharge of the channel also will be given, or you may have to assume accordingly, and you also know the V naught, so you will find the cross-sectional area. Again, one more drawback in this, you have to assume the slope later on. So you just find out the cross-sectional area for now, and later you decide the slope, etc. accordingly. So now you have got the cross-sectional area. So you should determine the actual velocity for this cross-sectional area and depth. So this actual mean velocity you will measure. Actual mean velocity is nothing but the velocity of the water keeps varying with depth. At the bed, because of so much frictional forces, it is almost 0. So at 0.6 depth, if suppose this whole depth is 1 meter, at 0.6 meter, whatever velocity of the water you get, that is known as the actual mean velocity. So you use Cutter's equation to determine this actual mean velocity. Cutter's equation goes like, it's a very big formula. V is equal to 1 by n plus 23 plus divided by S n by root r, and this whole thing is multiplied by root of rs. R is nothing but the hydraulic mean depth, which is area by perimeter of that channel, and S is slope, as you know. And N is rugosity coefficient. So depending on the channel condition and discharge, it varies from 0.02 to 0.03. If the channel condition is very good, it is at a lower value. It also depends on the discharge. Depends on discharge and channel condition. If the channel condition is very good, it is towards 0.02, and if the discharge is less also, it is towards 0.02. Usually Cutter's equation is used to determine actual mean velocity. Sometimes you use Manning's equation also, which is quite simpler than this, which goes like this, and N is the Manning's coefficient. Or sometimes people also use Chessie's coefficient. This equation is also similar to Cutter's equation, except that C is defined by this large value. So after this, you will get the actual mean velocity, which we can call it V. So if this actual mean velocity and critical velocity is same, then that is your trial depth. That is your depth and the area which you calculated. So that is your design, final design. If suppose V and V naught do not come same, you have to repeat it with a different depth, and you have to keep on repeating this process until V equal to V naught. So obviously in this there are a lot of calculations involved, because you keep repeating the process. So once you know the discharge, slope, critical velocity ratio and the rugosity coefficient, you can use something called Garrett diagram, where there will be a lot of graphs, and for these parameters you can easily come upon the optimum depth where V equal to V naught.
Are you aiming to crack ESE and GATE Civil in 2000?
Now let us see what are the drawbacks with this Kennedy's equation. The first and foremost thing is it is an empirical formula. It is just based on few experiments on the upper Doab canal system. He has come up with an empirical formula. It is not a proven formula. So that is the first drawback. The second drawback is that when the channel is just forming, I mean when water flows from various places or it is just flowing from a river, it would not attain its slope yet. It would be just forming. At that time, you cannot apply this because the parameters keep on varying. And also, one single factor m cannot explain the properties of silt. We saw that if the silt is coarser, you go for a higher m, and if the silt is finer than the silt in Doab canal, you go for a lesser m. There is a single factor which may not be sufficient to explain everything. And also eddies from the side of the channel is ignored. Only from the bottom it is considered. So some of these drawbacks were tried to be corrected by someone called Lacey. So Lacey's theory, and which he proposed 3 regimes also, initial, true and final regimes. We'll see about these things in the next video. Thanks guys for watching. Hello everyone. In this video we'll see about Lacey's theory. In the last video we saw about Kennedy's theory. This is just an improvement on Kennedy's theory. So what did Kennedy say? Kennedy said that a stable or regime channel is where no silting, no scoring take place. That is, the sediment neither gets deposited nor it gets scored. So that is what is meant by a stable channel according to Kennedy. But Lacey differed in his theory. What he said was true regime, that is true stable channel, can be achieved only if these 3 conditions are achieved. One is there should be a constant discharge, and another is the bed and the banks of the river should contain incoherent alluvium, which means loose soil that can be easily scored. The soil is very loose that it can be easily eroded and it can be easily deposited as well. So the soil type should be of this. And also there should be constant silt amount. And the silt grade also should be constant, that is the size of the particles, etc. So this is a very ideal condition which cannot be achieved. So he differentiated them into 2 types of regime. One is initial regime and other is final regime. Suppose let us say from the river the canal is forming and it has just started to form. So based on the etc., it will keep on changing its shape. If suppose it is a fine silt, it will be something like a semi-elliptical section, and if it is of coarser silt, the width will be even more larger. And depending on the silt size, silt's gradation, etc., the width keeps on varying until a stable regime is formed. So this is known as initial regime. Here also silting or scoring does not take place, but the width keeps on varying. So it appears to be in regime, but the theory of Kennedy cannot be applied here. So that is what Lacey says. Lacey's theory can be applied only to true regime or to final regime. Final regime is when, as water keeps flowing, this width keeps on varying and finally some stability is achieved where the depth, perimeter and slope is constant. Once this is achieved, it is in final regime. So Lacey's theory can be applied only for final regime and not for initial regime. Kennedy did not take into account this factor. So another thing which he differed from Kennedy was, Kennedy said that the eddies generate only from the bottom. So it is okay. It is the silt supporting power was kind of proportional to the depth. But here he says that eddies form from the side also. He did not ignore the eddies from the side. So the silt supporting power is proportional to the wetted perimeter. That is, the whole perimeter is taken into account. So that actually the eddies form from all the sides. So the silt supporting power, that is the silt which is in suspension, is by eddies from all sides. So it is kind of proportional to the wetted perimeter. And the silt factor which he applied was dependent on the size of the in mm. So he defined it as F equal to 1.76 root of d mm, where d is the average size particle in millimeters. Now let us see how to design according to Lacey's theory. So he provided an equation first for velocity. Velocity equal to qf squared by 140 to the whole power 1 by 6, where q is your discharge and f you saw it is the silt factor, which is equal to 1.76 root of average size dia in mm. So first you find the velocity from this equation. Then you find the hydraulic depth. Hydraulic mean depth R equal to 5 by 2 V squared by F. Then what you do is you calculate the area and wetted perimeter. So area, you know, Q is equal to AV, where you know the discharge, you know velocity as well from this equation. So you can calculate A. And wetted perimeter goes by the formula P equal to 4.75 root of Q. So you can find wetted perimeter as well. So based on area and based on wetted perimeter, you can assume side slopes like 1:2 or something and find the breadth and depth of the canal. So now the only thing left to find out is bed slope. For bed slope, he has given a formula S equal to F power 5 by 3 divided by, so F you know is the silt factor and Q is the discharge. From this you can calculate the bed slope. Now let us solve a problem which came in IES exam. It's a simple straightforward problem where they have given the velocity designed by, according to Lacey's theory, is 0.88 meter per second and silt factor they have given as 1.1 directly. So what will be the hydraulic mean depth? You know hydraulic mean depth is 5 by 2 V squared by F, which is 5 by 2 into 0.88 squared by 0.1. If you solve this, you will get 1.76 meter. So it is a simple, straightforward problem. Now let us see what are the disadvantages associated with Lacey's theory. One is, as you know, like Kennedy, this is also empirical formula and a single factor F is not adequate. So just based on size of factor, F has been defined. So it is not adequate to represent the silt properties just by one equation. And also he did not define about silt grade or silt charge, how to take into account and all that. And also he did not talk about concentration of silt. So even Lacey's formula has some drawbacks like Kennedy's. This question I leave it to you. So this was also asked in engineering services exam. So they are saying consider the following statements by Lacey and Kennedy. So the first statement goes like theoretical concept of silt transportation is same in both. The second statement is saying that Lacey improved upon Kennedy's formula. Third statement is there are no defects in either Lacey or Kennedy theory. So which of the statement is true? So you can answer this in the comment section. Thanks guys for watching the video.